Hello, geometry students. That's right, I am going to do it. I'm going to do it. I am going to ruin triangles for you. Triangles have always been these easy figures to work with. What's that? The angle sum theorem, where all of the angles of a triangle have to equal 180 degrees? Piece of cake. Identifying acute and obtuse or right triangles? Easy. Even the triangle congruence postulates and theorems that we've been working with so far aren't really that hard. There's an angle, another angle, and a side that are congruent. That means that the triangles are congruent and the corresponding parts of those triangles are congruent. Now, I'm going to be honest with you. The reason that those things were easy for you is because there's things that you've learned before. There's nothing new there. You've been working with those in other classes. The things we're going to be working with on triangles today, either you probably haven't heard of these before, or you've heard of these so obscurely that you probably don't remember them. And that's what makes this lesson hard. In reality, this lesson really isn't all that hard to grasp. I'm probably not going to ruin triangles for anybody, but I am going to make things just a little bit more complicated from where we are as we talk about some terms related to parts of a triangle. And we're going to talk about parts today like the median of a triangle. What is a median? A median is a special segment we can draw in a triangle that starts at a vertex of the triangle and goes to the midpoint of the opposite side. Now notice I didn't say it goes from vertex to vertex. If I was going from vertex to vertex of a triangle, I would just be drawing a side of the triangle, because there's only 3 sides and they're each a connection of consecutive vertices. And there's no way to connect vertices in a triangle without drawing a side, right? So the only way to connect a vertex to something else that's sort of like a vertex and that it's sort of like a center of something is to draw to the midpoint of the opposite side. Now, if a triangle has 3 vertices, there's going to be 3 medians. And we're going to see what those 3 medians look like in this lesson. Now, those medians, when I draw them, are going to cross each other, and they actually cross at a single point for any triangle. We call the point of concurrency. Concurrency is a fancy word for intersection, and we use it when more than 2 lines intersect. So there's going to be 3 lines intersecting at the centroid at the same point. We call it those concurrent lines because there's 3 of them. It's the point of concurrency of the 3 medians. And I'm just going to tell you, anytime you draw a triangle, your 3 medians are going to intersect at a single point. And then we have this centroid theorem that recognizes that actually there's a mathematical relationship in every centroid. The centroid is always 2/3 of the way across the triangle from the vertex. So if I were to draw segment CZ, for instance, if I started from the vertex, not from the midpoint of BA, but if I started from the vertex over here, and I measured the length of the centroid, point P would be 2/3 the length of the centroid, and then this remaining PZ would only be 1/3. Okay, so this between the midpoint and the centroid is 1/3 of the way across the median, and from the vertex to the centroid is 2/3 of the way across the median. And that's what this centroid theorem is saying. This actually makes it really helpful to calculate centroids, but I'm actually going to give you an even easier way to calculate centroids. It's probably a sneak peek at a future way in our book. But it's very reminiscent to the midpoint formula and very easy to use, and we'll be looking at it in the lesson practice. For now, let's talk about the other type of line we're going to learn about in this lesson, that is the altitude. This is nothing new, because we already talked about the altitude. To find the area of a triangle, you use the base times, not the height necessarily, but the altitude, and then you multiply it by 1/2. The altitude is a perpendicular segment from a vertex to a line containing the opposite side. And I would love it if I could just say the altitude of a triangle is a perpendicular segment that starts at a vertex and goes to the opposite side of a triangle. The problem is anytime you have an obtuse triangle, your altitudes are going to be outside of the right triangle, or at least two of your altitudes will be outside. And how do you draw that? Well, you actually have to draw the whole line containing the opposite side, and then your altitudes will be perpendicular to that line. We'll take a look at what I mean by that in just a moment. But when your altitude crosses that line outside of the triangle, you need to extend a side of the triangle to draw your altitude. Then we're going to talk about one more point, the orthocenter. The orthocenter of a triangle is the point of concurrency of the three altitudes. So the altitudes are all going to cross at the same point. Interestingly, they only cross at the same point inside a triangle for acute triangles. We're going to see that there's a special case of what happens in right triangles, and for obtuse triangles, the altitudes are all going to intersect outside of the triangle. All right, that's almost all that I need to say. I just want to point out there's not much I can say about orthocenter, but I have one more fun fact about the centroid of a triangle. Sometimes the centroid of a triangle is known as the center of gravity of the triangle. And if you were like making a mobile and you were hanging triangles from your mobile, if you put a hole in one of your triangles at its centroid, you could hang the triangle from the centroid and then spin it around in any orientation, and no part of it as you spin it around will be heavier and pulled down harder than any other part of it. So you could actually spin it around on its centroid and it will balance in any orientation. Whereas if you had a point that's not the centroid and you tried to hang it from that point, part of the triangle is going to be heavier, so that side is always going to fall toward the ground. At the centroid, there's an equal amount of mass surrounding the point on all sides. So just a sort of interesting tidbit about the centroid. I don't know if you'll be able to use that for anything, but kind of nice to know. All right, let's take a look at some practice problems. In triangle ABC, AD equals 5 and EO equals 4.2. We need to use the centroid theorem to find the lengths of OD and, okay, so OD is this little guy right here. Notice that OD is not connected to a vertex. That would be OA. OD is connected to the midpoint. So that's going to be a 1/3 the length situation. And BE is the entire median. But I know the length of EO, which again is the length that's connected to the midpoint, not to the vertex. So that's going to be another 1/3 length. So let's go ahead and figure this out. Use the centroid theorem to find the lengths of OD and BE. Okay, so for OD, OD is 1/3 the length of the median. 80 is 5. So 5 divided by 5 times 1/3 is probably the best way to think about it, right? Because I'm multiplying it times the 1/3 of the median that OD is. 5 times 1/3 is 5/3. 5/3 is, let's see, 1.67, I believe. So let's just see if we got that first part right, 1.67. And then for the next one, I need to figure out what BE is, that whole one, and I know that EO is 4.2. So for the next one, I'm going to do 4.2 times 3, because 4.2 is 1/3 of the length of the whole median. This is 2/3 of the length. This is 1/3. 4.2 times 3 is 12.6. Let's see if we got that one right. All right, let's move on to more fun things. Now, letter B asks us to use a coordinate plane to find the centroid of JKL with vertices -9,1, -1,5, and -5,9. And what it's saying is we should probably use a coordinate plane and actually graph this on graph paper. And that's what I would suggest you do for a problem like this. Me on the computer here, I don't have easy access to graph paper. So I'm going to use the computerized version of graph paper after I show you something kind of cool. I'm going to tell you there is a formula for calculating the centroid that's very, very close to the midpoint formula for a line segment. And what it is, you add up all of your x points and then divide by 3 to find the average. And then you add up all of your y points and you divide by 3 to find your average. And the x points divided by 3 gives you the x coordinate of the centroid. The y points divided by 3 gives you the y coordinate of the centroid. Let's see if this works. We'll do this, and then we're going to test it experimentally using GeoGebra. So -9 plus -1 plus -5 is -15. -15 over 3 is -5. That's my x coordinate of my centroid. 1 plus 5 is 6, plus 9 is 15. 15 divided by 3 is 5. That's my y coordinate of my centroid. Well, let's see if I'm correct. Yes. So that formula works, but let's see if GeoGebra gives us the same results. Okay, so here I am on GeoGebra. I'm going to click to start GeoGebra. And I don't know if you know this, but if you click on Tools and then scroll down, you get some pretty awesome geometry tools right here on GeoGebra. Now, I'm just going to click and make points where I'm supposed to for this problem. I see they're at -9, 1, -1, 5. So let's do -9, 1, -1, 5. I have to zoom out just a bit. Let's see if I can find that point. Okay. And then the last one's at -5, 9. Let's scroll up. So here we'll just do that. And we'll go to -5, 9. -5, 9. All right, now, this is not a triangle yet. I need to make this into a triangle. So what I'm going to do is I am going to go down here to lines, and I'm going to click on segments, and I'm going to connect these guys with segments. There we go. There we go. There's our triangle. Now, we need to try to figure out where the centroid is. So what I'm going to do is I'm going to click up here and choose to find a midpoint. And then if I click between 2 points, it'll automatically put the midpoint on that line of the triangle. Okay, now I can draw segments from my vertex to each midpoint to get each median, and I can see where all of the medians cross. Beautiful. And then the last thing that I need to do is go back up to put a point on the intersection here, and that is my centroid. Now, let's take a look and see if I've got this correct. I'm going to go back up to here, and it looks like the centroid is at -5, 5. So my formula worked. Now, let's just have some fun. What happens if I drag the vertices of this triangle around? Notice that as I change the way that this triangle looks, here's an obtuse triangle, here's probably roughly a right triangle, and then I can make an acute triangle. No matter what I do to this triangle, the centroid is somewhere inside the triangle. And it's always going to be, for each of my segments in here, it's 2/3 away across from the vertex toward the midpoint of the opposite side. So this length here is 2/3 of the total length. But do you see how it stays inside while maintaining that relationship? Okay, we'll come back to this in just a little bit.